Okay, so I'm going to go through two examples here for finding the molecular geometry. So the first thing I'm going to start off by doing is creating a Lewis diagram. So here's my order for doing a Lewis diagram. I first find the element which has the highest bonding capacity, which is also the element which has the lowest electronegativity. In this case, it's going to be carbon, right? Carbon can form 4 bonds. Chlorine and bromine can each form 1. So carbon is the element I'm going to place in the middle. Next, I take my other elements, 2 chlorines and 2 bromines, and place them around the central atom. Okay, all of the shapes that we're looking at are shapes with a central atom and then terminal atoms, so or outside atoms. Next thing I'm going to do is total up the total number of valence electrons. So carbon has 4 valence electrons. Chlorine has 7, but there's 2 chlorines, so that's 14. Bromine has 7 as well, for a total of 14. So for all 5 of these atoms, there are 32 valence electrons. The reason why I'm doing that, it's because the valence electrons are the ones that are involved in bonding. So they're the ones I have to figure out here with my Lewis diagrams. Okay, my first step, I'm going to draw a straight line representing a bonded pair of electrons. So I've used up 2, 4, 6, 8. Next, I'm going to go to the outside elements and complete their octets. Okay, now I'm going to check to make sure to see how many electrons I've used. So each of these 6 there, 6 there, 6 there, 6 there, that's 24, 26, 28, 30, 32. So I've used up all my valence electrons, so I can't place any more. And now to make sure I've got the correct structure, I make sure that every element has a completed octet. So chlorine 8, remember an octet, lone pairs plus bonded pairs, right? Chlorines, bromines, they each have an octet. Carbon, 2, 4, 6, 8, an octet. So we have a stable molecule, so this is a good Lewis structure. And now I look at the combination of bonded pairs and lone pairs. And a shape which has 4 bonded pairs and no lone pairs is going to be tetrahedral. So this is a tetrahedral shape. And there is, I'll draw the shape diagram C. The shape diagram has dashed lines to indicate going backward, back into the plane of the paper, and wedges to go out to the front. So there's a tetrahedral shape, okay? I figured out the shape based upon the combination of bonded pairs and lone pairs around the central atom. That is Vesper theory. Okay, let's do a second example. XeBr2. So my first point, I will start off by totaling the number of valence electrons. 8 for xenon, a noble gas, plus bromine, each has 7, and we have 2 bromines. So there are a total of 22 valence electrons. So that's what I have to work with to complete all the outer valence shells. Now, noble gases can throw people off because you don't think of noble gases being able to bond, but they can access higher subshells. So the noble gases, if you see them bonding, they will typically be the central atom, xenon, krypton. The other thing to remember is that the halogens are always going to be the outer or terminal atoms. because they can only form one bond, they have to be on the outside. Okay, so once again, my next step is to form a single covalent bond between the outer atoms and the central atom. So I've used up 4 electrons, and now I'm going to start filling the valence shells of the outer electrons. So I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this time I've completed the outer shells, and I've only used 16 electrons. Next, I go to the central atom. I have 6 atoms left, or 6 electrons left. 1, 2, 3, 4, 5, 6. Now, you look at this now and you see that xenon has 2, 4, 6, 8, 10 valence electrons. So that's what's called an expanded octet. And an expanded octet is allowable for elements in periods 3 or higher. Reason for that, elements in period 3 have electrons at the 3rd energy level, and so they can expand their octet by hybridizing and accessing those 3D subshells, so they can access more spaces for those electrons to be. For elements in period 2, it's just too big of a jump for them to access those subshells. Okay, so now I've got the structure, and I need to figure out the shape. So I would recommend starting off using the chart. In the chart there, the key columns in the content section of the course has a column where it says the total number of electrons. So 2, 4, 6, 8, 5 total pairs of electrons and 2 of them bonding. And if that's the combination, we end up with a linear shape. And just so a reference here, the reason why we have a linear shape here is because I'll just draw those unpaired electrons. Those are in the plane, and you imagine the 2 bromines are in a vertical axis. Vesper theory states that the arrangement will always maximize the distance between all the pairs of electrons, and bonded pairs have more repulsion than lone pairs, so they're going to spread themselves out further. Let's quickly pop over to a simulation, and you can see this again. Not sure whether you can see this in the video, but this is from the website PHET, P-H-E-T. So it allows you to add pairs of electron or bonding atoms, and you can kind of see the shape. Okay, so 2 pairs of electrons, they're all bonding pairs. We have a linear shape. If I add a lone pair of electrons, so a non-bonding pair to the central atom, what do we have? A bent shape. Hey, that's like water. Add another bonding pair. What do we see? Oh, trigonal planar. 3 bonding pairs and no lone pairs. Oh, lone pair added. 4 pairs of electrons. 4 pairs of electrons, 3 bonding. There we have trigonal pyramidal. Let's look at the shapes that we just did. Oh, there's tetrahedral. 4 bonding pairs, no lone pairs. Note that it's a symmetrical shape, the most common shape in organic chemistry. And we just did the linear shape, but so here's a linear shape with no lone pairs. We did a linear shape with 3 lone pairs. Here's the example we just did. So do you see how they spread themselves out? The bonding pairs are on the vertical axis here. And then we have the 3 lone pairs that form basically a triangle in one plane here. The reason why they spread themselves out this way is because this maximizes the distance between the pairs of electrons, which minimizes repulsion. So I would highly recommend this simulation if you're having trouble with molecular geometry. And it's great for kind of visualizing these structures, and you can kind of move things around and you just get a really good sense of the shapes of the molecules.